Okay, so this is the second part. So if you still have some questions for this morning session, you can answer now. No, that's okay. That's digested, and so we can go further. And further means part 2, which is quantization. Okay, so I will not go into the machinery of quantization and all that. I mean, the basic that you can find in many books. Okay, just recall a few things, and then use this modal approach to see what is we can exploit from that. So usually, when you look at books, the way that quantization is performed is first through this traveling wave basis of 2Ls, yes. Traveling plane wave basis. So the first one that I mentioned this morning, the one which is using the modes UL of R and T, which is the polarization, and then the usual wave factor, okay, phase of the wave here, okay, with the restrictions on the values of KL and omega L and epsilon L that I mentioned, okay, in order to have a basis in the volume V. So when you do that, then it's the field that I wrote this morning, which is a classical field, okay, as a sum of EL, UL of R and T. Then when you want to quantize that, you have to transform what is a C number, okay, which is this one, which describes the classical fields on the basis, into what is people call sometimes Q number, which is the operators. Okay, so you have now to construct an operator in the same way as when you do the same thing for position and momentum of an electron, of a particle. Then you go from the position and momentum of the particle into position operator and momentum operator with some rules of commutation. Here is the same. Now what I define is the operator field at some point in time and space. So it is in time and space, meaning that I'm dealing with so-called Heisenberg representation, in which the operators are evolving in time and the states of light are fixed, okay? They are equal to their initial values. Okay, so I will not go to the detail of that, but it turns out that if you do that in this specific basis, and only in this specific basis, then you can write that as in this way. Okay, the field operator has a decomposition over the same basis, the UL traveling plane wave basis, but instead of having in front of it a number, this complex amplitude, you have an operator, which is that. So this has a dimension of a field. So this one also has a dimension of a field. And the field quantity, scaling factor, is this EL. So it's a field, a quantum field unit, which is, so I don't demonstrate it. You find that in all the books. Okay, this is a so-called single photon field. Okay, the field characterizing the amplitude of the field for a single photon wave. And you see that it depends on this L3, on this volume in which you have put everything. So meaning that if you have no volume evolving in free space, this quantity is not very physical, okay? So then you have to go to something more measurable, and usually when you go to measurable things, then this L3 cancels, okay? Or you have a real cavity, so this is called cavity quantum electrodynamics. And in this case, this is the volume of the cavity that you are using. And if you want to enhance the quantum effects, you have a big electric field for a photon, means that you have to work with very small cavities. So this is nano photonics things at this level, okay? Okay, so this is scaling factor. So then the other part here is an operator, but an operator which has no dimension, dimensionless. And the operator has been written in such a way that the commutation relation, which is just the foundation of everything. So when I write this, I can then go out, it's finished, okay? The quantum optics is finished by that, okay? So which is equivalent for fields of the commutation relation, xp equals IH bar for electrons, for particles. Okay, sorry. So this has nothing to do with harmonic oscillators, okay? But finally, it turns out that the operators, which are the basic tools of quantum description, are expressed in terms of these operators, and these operators turn out to have the same commutation relation as harmonic oscillators. Okay, so the mathematics is the same as the one of the harmonic oscillator. Not on for a single one, but each harmonic oscillator for each mode, for each traveling plane wave mode. Okay? So with these kind of operators, you can build other quantities, other observables. The most important one, of course, is the energy, because with energy, you have the Schrödinger equation and all that. And energy corresponds into the quantum domain to Hamiltonian operator. And to obtain it, you start from the classical expression of energy. You know, it's integral over whole space, over V space here, of epsilon 0 E squared plus B squared over 2 mu 0. So if you express the E squared as a function of the mode, the B squared as a function of the mode, and all that, you crank all this thing, and you find finally that this is sum over L of H bar omega L. So it's important. So the energy is expressed as a sum of energies of the different modes, okay? So which is nice. You can then have an energy per mode. And this energy per mode has this operator that we call number operator, which is this one, okay? And of course, there is the scaling here is H bar omega L. You can do the same with P, with momentum. Momentum is integral over whole volume of E cross B over mu 0. And, okay, and then also you decompose the E and the B in the modes, and then you find out that finally the momentum operator has this expression. Okay, it's a combination of momenta for each mode here also, and in front of it you have the same number operator. Okay, so this is very simple. Then now one has to define not only operators but states of light. And the easiest one is what is called the vacuum state. So I will write it this way. The vacuum state is the one for which you have AL vac equals to 0 for any L value. Okay, the state of light for which the annihilation of an operator gives nothing being the number 0, okay, here. And this defines this state of light, which is strange, state of light which describes no light, okay? As we will see, as you know already, because this operator, which is a number operator, Why do we call it number operator? Because the eigenvalues of this operator, it's well known when you work with harmonic oscillator, material harmonic oscillator, they are the integral digits, okay? 1, 2, 3, 4. So it's a number operator. Then from the vacuum, you can define the n. So this is the way I wrote it. N UL. Okay, so it's n because it will be negation of that with value n. But I put already here the mode. It will be n photons in the mode UL. Okay, and this is from vacuum. You can build it by applying and with some scaling factor and of a vacuum. Okay, you start from your vacuum state and you apply n times the operator A dagger, and this A dagger creates n photons in the mode. So this is a n photon mode, what is called Fock state or any number state, anything like that. And in particular, the one I can write 1 UL, okay, which is the first of this one, is A dagger vac, A dagger L, okay, it's a single photon in mode UL. Okay, it is an eigenstate of NL, and therefore it is an eigenstate of energy and eigenstate of momentum. Okay. Of H first, which is the most important thing, and P. And of any quantity which depends upon A dagger and A through the A dagger A thing. Okay? Okay. So we'll not go into the details. Why do we call it single photon or n photon? Because the energy grows by equal quantities h bar omega L, and the momentum grows by equal quantities of h bar k L. Okay. So we can say that the photon has an eigenenergy h bar omega L and eigen momentum h bar k. But we have to add that it is true for single photon in the mode UL. Okay, now let us change the mode here to 2. And see what happens. So in order to change the mode, I take a unitary matrix, a unitary transformation UM. Remember that we use the same for changing the mode at the classical level. So it's the same here. You need to work on the space of modes in addition to the space of states that is just coming now. And the simplest way to write it, to write things, is to write the create. So, okay, you know also that this is called creation operator, A dagger, because it creates from vacuum 1 photon, and B and A. This one is annihilation operator because it destroyed photons, goes down in the ladder of photon number, and when you are at the level where there is nothing, no photons, then it goes down to nothing, to 0, number 0. Okay, so if I define a new operator that I call B dagger M as being the combination over L of ULM, okay. So, okay, I remove this M here because M has two meanings, mode and the index M for labeling. Okay, so you know that this U acts on the mode Hilbert space. Okay, and then so I take this kind of combination. Okay, so it's a linear combination. It's just an application of the unitary matrix U to the column vector of A dagger for each traveling plane wave modes. Then I don't want to to make all the calculations. You can do them by yourselves. From that, and the fact that U is unitary, you can calculate the commutator, B dagger, in two different indices. Okay, so you combine that, and you use the fact that it's a unitary matrix, U, unitary. And what you find is delta M prime. Okay, so when you make this kind of unitary transformation on the operators A, you find operators B which have the same commutation rules as the A's. Okay, so you go from something which enables you to define photons to something which still enables you to define photons. Yes?
Why in the field operator it's the annihilation operator that comes in the integration operator?
I have no idea, but this is the way it is. So in some ways, the creation of, so something that I have always in mind is that A, L, is field, is wave. So the A operator describes the wave aspect of light, whereas A dagger L describes the photons, the particles. And this is all the mystery of quantum optics in some way, okay? So when you have the number, you take the square root of the number, so to say, I don't know, and you find a field, okay? But square root of the number, of course, gives a field because the square root of E squared is E, but it gives a field with its phase and everything, with its coherence properties. But I have no further idea on that. Of course, this is E plus, so this is a complex field, okay? The one corresponding to the analytical signal I was beginning with, okay? But if you want to write the real field, of course, it is the sum of E plus plus the conjugate of E plus. So for operators, it's E plus plus the Hermitian conjugate, okay? And this, for the real field, okay, you will have this plus the conjugate, so plus the same terms, but with A daggers, okay? So the real field is a combination of this sum for A's and the same for A daggers with a complex conjugate here. Okay? But fields are linear with respect to the operators, whereas energies and numbers and photon parts are quadratic in that, which is also normal because the energy is E squared. So it's quadratic with field. Okay. So now, if I do that, I have a new set, so I can write. So here also, I can still write the same field, E plus, but now in terms of the new annihilation and creation operators, B. Okay? And if you take that, put it in this expression, make all the machinery, so I don't want to spend too much time on that. You find finally, where is it? That, okay, it is the sum of M, of Fm, Bm, F, M of Rn. Okay, so these are exactly the same structure as this one. I just have to replace the scaling factor by the new scaling factor F. I have to replace the A annihilation operator by a new annihilation operator Bm, and I have to replace the traveling plane wave mode, UL, by a new mode. Okay, and this mode is simply Fm is 1 over Fm sum of ELU LM UL of RNT. Okay, so it is the old modes, the UL, the traveling plane wave modes, on which you apply the unitary transformation, and then you have a little problem of scaling factors. The old scaling factors, the new ones are here. Okay, so this is a new mode. Fm is a new mode basis. And it is obtained from the old one, the UL, just by applying the same U transformation that was introduced this morning, okay? So here you have everything. The new thing is that you have a mode transformation not only acting on the mode, but acting on the operators. This is the new part. But it's still the same game, okay? Okay, perhaps you want to know a bit more about FM. FM is a scaling factor, which is sum over L of EL squared UL. It's a bit complicated expression, UML. Okay. Why is it complicated? It is related to the fact that EL squared, the scaling factor at the beginning, is something depending on the frequency, where it is here. You see EL depends on L through the frequency omega L. So when you make this kind of sum, this is inside, okay? So you cannot simplify things on the related to unitarity, because unitarity is here, okay? And you have this factor. It's only if ULM does not mix frequencies, does not mix frequency. Okay, so the transformation mixes the different k vectors corresponding to the same frequency. So it mixes directions of propagation, but not frequencies. In this case, you can put this on the other side here, okay? And you have something simple, because this is unitarity that you can use. And in this case, okay, FM is equal to EL in this case. Fm is equal to EM. Because then this is here, and this is delta LM. Because U minus 1 is 1. It's delta, okay? So the scaling factor is the same, unless the mode transformation mixes frequency modes, which is possible, of course. Okay, and in the case where it doesn't, okay, here also you can put this on the other side, okay? And in this case, FM also has a more simple expression, which is just sum over ULM UL. So in the way I wrote it before is that F is U in terms of column vectors. Okay, so this is exactly the expression that I used this morning for mode changes. Okay, so we are back to mode changes, but the mode changes operate also on the operators. Okay, the operators are also changing. So annihilation or creation operator in a given mode basis is not equal to the creation or annihilation operator in another mode basis. Makes sense? Okay. So you have that in mind. Of course, it will be interesting to relate the different things. So we have related already here operators. Now we have to relate vectors, okay? Quantum states. Quantum states, the simplest one is VAC. So this VAC was defined as the one giving 0 to any annihilation operator. So what is now BM acting on VAC? Okay, now I want to see what is the action of B on the same VAC. Okay, the VAC which has been defined for the plane wave basis. Very simple. BM here, if I remove the dagger because, okay, I take the complex conjugate of this expression, I will have B equal to sum of U LM conjugate A. Okay? So it's a linear combination of A's. So this BM VAC is a linear combination of AL VAC. AL VAC are all zeros. Zero. Okay? So the vacuum defined as the state giving 0 for any annihilation in the given basis is also the state giving 0 for all the modes in the other basis. So the two vacs are the same, okay? The vac defined in one basis, in the other one. So the vacuum state is intrinsic, let's say. Is intrinsic, we'll come back to that very often, meaning that it doesn't depend on the basis of the mode that you take, okay? No photons in a given basis is no photons in other basis. This is not obvious, because as you will see, it's not the case for all the other modes. So it's a good start. Now let us look at single photons. So one in mode UL, no, in mode FM. Okay, it can be defined the same way. Okay, as A, now B dagger M, acting on the vac defined in the given basis, but it is the same as the vac on another basis. Okay, and big dagger M, I know this expression here. So this will give me sum over L of ULM 1 UL. You see the single photon in the new mode is a linear combination of single photons in the other basis. Okay? So what is important to see here is that a single photon is not defined independently of the mode. Okay, a single photon is a single photon in a given mode. A single photon in a given mode, because when you change a mode, you change the expression of the system. Okay, so a photon is not a little ball. Okay, because a little ball is a little ball, whatever the way you look at it. Okay, here it's. I prefer to call it an excitation, the smallest excitation of a given mode, okay? Which has particle properties. It can be localized. It gives us a single click on the detector and things like that, okay? But, so it's a particle-like excitation of a given mode. And since, for this reason, it has not always the same properties as the single photon here. So is it an eigenset of energy? Not always. Not always eigenstates of energy. Because if you are specifically in this case where the ULM mixes different L values, okay, so it will mix photons of different frequencies and then photons of different energies. It will mix traveling wave photons of different energy, each one being eigenstate of the energy. But of course, if you make a combination, it's no longer eigenstate. Okay, so it isn't. So photon equals h bar omega. It's not always true. Okay, when you look at what people call single photon wave packets, which is this case of this kind of things. Okay, so mixing of components of different frequencies, then this one is no longer h bar omega, okay? It is not an eigenstate. Of course, its mean energy is the mean value of h bar omega, but it's enough. No, it's not eigenstate. It's not always eigenstate of P, of momentum. Same reason. If you mix different K values, okay, of course, you will not be any longer eigenstate of a given K. Okay, for example, standing wave, where you mix K and minus K, of course, have no momentum in a given direction because it goes in two directions at the same time. Okay, so it's not always eigenstate of P. It's not always eigenstate of L, angular momentum. I have no time to do that. But if you take as a mode a Laguerre-Gauss mode, okay, and take a single photon in Laguerre-Gauss mode, you find that it has angular momentum, but only these ones, only the ones in Laguerre-Gauss mode. And what else? Okay, there are many others. So this is for single photon. So if you remember what said Newton a long time ago, is light made of small objects emitted by shining substances? No, it's not a little thing which is independent of what is around, okay? There is still this wave aspect which is related to the mode in the photon. Okay, so this is for single photon. Then, of course, you can look at n photons, where the n photons in mode Fm. Okay, just the extension of that. You use this expression. Where is it here? So it's B dagger m n times you over root of n acting on vac. Okay, so I stop here the expression, but you see what you have to do. You replace B dagger m by its expression, its linear combination of A daggers. Then you have to put that on the power n. So it's a lot of terms then when you do that. And you have to be careful because the A and A dagger do not commute. So you cannot group all the terms together, okay? You cannot use the Newton law, okay, which is valid only for commuting things. So it will be, for 2 it's easy to write, but then it's more and more complicated. Okay? So you see how to deal with the mode change, but you see that a lot of properties are changing with mode change. Okay. So an important consequences of that I write because it's important. Quantum state of light psi, so it can be any of these and more complicated ones, has different form, may take different forms in different mode bases. So if you think, and I think we have to be on this side, that psi completely describes the object, the quantum object. Of course, the quantum object psi looks differently if you use a given basis or another basis. So one example is the two-photon state. There are many, of course, but this one is the two-photon state in a given basis, so that I call psi2 because it's a two-photon state, form of one photon in mode F1 and one photon in another mode F2. Okay? Now let me change mode and use as new mode F plus or minus, which is the symmetric and antisymmetric combinations of the previous ones. Okay? No, not modes, it's classical quantities. Okay? So for example, if you think of polarization modes, so the F1, F2 can be the two orthogonal polarization, then F plus and F minus will be the one at 45 and minus 45 degrees. But it can be any other. It can be K and minus K, and okay, anything. But if you use the rule which I take here for the single photon in this basis and make all the little calculation, you find that the same state, psi2, is 1 over root 2, do not make mistakes, 2 on F plus, 0 on F minus, minus 0 on F plus, 2 on F minus. Same state. Okay, so here we say, okay, I have a factorized state. And here you say what? I have an entangled state. Okay, so entanglement and factorization are not intrinsic in this meaning. They depend on the basis you take. Okay, so when one is speaking of entanglement, one has to be careful. Entanglement has a kind of intrinsic physical meaning when you have a bipartite system. You can define at the beginning Alice on one side, Bob on the other, okay? And then you have entanglement between these two. It means that you are allowed to make changes of modes of representation, but not allowed to mix Alice and Bob, okay? It's called local transformations. Here, it's a single system, okay? So you are allowed to make any transformation you want, and of course, the transformation which is here mixes the two sides. And then, in this case, entanglement, something which appears in some bases and not in other. We will see later also that is important for the following. Okay. Then here I have a message, so I write my message. So 2, 4. Is it 2? Yes. The double linearity of quantum optics so it's, let me go back to the field E plus, which is a sum of Fm, Bm, Fm. Okay, I don't write the R and T, so the field operator at some position is decomposed over the mode basis with an operator and a scaling factor, okay? So we have two parts here. We have the quantum part and the optics part, let's say, okay? So in this side, we have the Hilbert space of states, of quantum mechanics, okay? And here we have the Hilbert space of Maxwell equations, so derived from the linearity of Maxwell equations, Hilbert space of modes. We have seen that we are able to work with unitary transformation here. Of course, we know that there are unitary transformation on the quantum part, so it's well known. Okay, and here in the same expression we have both. Okay, this is new in some way because it was not present in the classical field. This is not new. The Fm part is the same in classical optics and quantum optics. Okay, the shape of things, which is here, of quantum things, is the same as the shape of classical things, classical waves. Okay, why not? But okay, now there is a game to play between these two parts. Okay, well, you can either change here or both, but still you have to do it in such a way that it preserves the combination of the two, which is the one giving the field, which is independent. This part, of course, doesn't depend on the way you decompose it. Okay, so this is a kind of interplay that will be fruitful. I think I will try to convince you. Okay, so what I can do now is try to define intrinsic quantities. So it's an important part, so it deserves a new part. Okay, intrinsic quantity. So let's see, I change my column. So these are the quantities which are defined independently of the choice of the mode basis. Okay, so it has more physical meaning than what depends on the basis. For example, I know already that vacuum state, vacuum, the obscurity state is intrinsic. Okay. What else? Okay, there are not so many. 3-1 total photon number. Okay, so if you start, let us start from the basis of traveling plane waves. So we can define an operator which is the sum over all modes of the number of traveling wave photon number, okay? And of course, I will call that n tot. And so far, it's n tot in the basis of traveling plane waves, okay? But then I can use what I erased here, the relation between the A's and the B's through the unitary transformation U, okay? And as you see here, what I have here is a kind of distance, the sum of all the square moduli of all the components. So it's sum of x squared. So it's a distance, and distance is independent of unitary transformation that you can do. Okay. So this is just a very fast demonstration. As of course, you just have to put the expression of A daggers in terms of the B's daggers, the expression of A in terms of the B's, put everything, use the unitary character of the transformation, and you find that it is equal to that. Okay? Total number of photons in one mode, on one basis, is a total number of photons in another one. But it's not true for any component, okay? But the sum, yes. So it means that the photon can be redistributed, different bases, but this is what we see here. Here it's a two-photon state, and the n tot is 2. And here also 2, 0, 0, 2 is still two photons. And this kind of demonstration can be applied to a vac also. Vacuum is a zero-photon state. It's a zero-photon state in all bases. And there is a single one. Okay. So what is important is the next one is a single photon states. So a single photon, I will define it as an eigenstate of n tot with eigenvalue 1. Okay? This one is intrinsically defined. It's defined with respect to an operator, which is an intrinsic operator. From that, it is, so I will call it 1, psi 1. And it turns out that if you work demonstration on a given basis, that it is given by this kind of combination in mode Fn, or Un if you, let me put Fn. Okay, I take a single photon in a given mode, then I make a linear combination of these photons. Of course, n changing, it will be in different modes, okay? And of course, it has to be normalized, so the sum of Cn squared is 1. Okay? So this is a state which looks, which is single photon, but not at all single mode. Okay, because it spans over, so it depends. Of course, if you take C1 is equal to 1 and C2 and all the other 0, it will be single mode, but it looks not single mode. But now let us define a new mode G1, which is a sum of Cn Fn. Okay, so I take the mode in which I have defined my photon, and I take the same combination, linear combination, as the one that, of the mode. So here I play my little game here, okay, playing with the two parts, this part and this part. Here I change the state, and here I change the mode, but in the same way. Okay? So it is easy to show, because this thing is B dagger, if I call B dagger the operator corresponding to the mode F. Okay, so this is B dagger acting on vac. Okay, so we'll have a combination sum of Cn B dagger, n. Okay, which correspond to a creation operator in this mode. Okay, I don't want to make the demonstration because I think the time is running. But you have the flavor of the demonstration. You can do it more precisely if you want. But psi 1 is also in this new basis of G1 and I complete by G2, which are orthonormal to the first one. Okay, it's a new basis. The first element has been defined with respect to my problem, and all the others, I take them as orthogonal to the first one. So I construct a basis. And in this basis, psi1 is 1 G1. Okay, if you are not satisfied with my very fast demonstration, do it by yourself. Okay? So what does it mean? It means that something looking multimode, highly multimode, if you have a lot of values of Cn and many modes, if you take the right basis, okay, then it's single mode. So all single photon states, so I will write that somewhere. Single photons are single modes. Are always single mode states. Meaning that there exists intrinsically single mode, even though they don't look like that. Okay, it means that there exists a basis in which they are single mode. Okay. Okay. So perhaps this is the reason why people working at single photon states and all that, they didn't consider a lot the mode problems, mode issue and mode point of view, because it's always in a, okay, so the mode and the state is the same in some way. So this F, this G1, which has been defined here, has a spatial and temporal variation, which is well defined, because you know well the Fn, you know well the Cn. And this Fn, G1 mode, is in some ways a wave function of the photon, because it will give the temporal and spatial shape of the state in which the photon lives. Okay, so if you look at the probability of getting click in a photodetector, its variation with R, you will find that this variation is G1 squared. So G1, like psi squared for the electron, G1 squared of R and T is a kind, I put quotes because a lot of people do not like that, the wave function of the photon. Of course, it has not all the properties of the wave function of an electron. It's a bit different, but it gives many properties which are the same as the one that you can get from a wave function of an electron, position and correlations and all that. But for example, if you take the famous interferometer with a single photon, okay, so you have a photon here arriving on one port of a Mach Zehnder, let's say, okay. Then if we consider photon, you say, oh, it goes on one side or on the other, okay. And then we combine after, and the properties of what goes out are given by both arms. So it looks strange in some way. But if you take that, what is the mode in which this photon is? Single photon. It is a mode corresponding to the whole interferometer. So it's a mode which is the sum of the two paths. Okay? So the photon which is defined here is not a photon taking some paths. It's a photon which is present in the two arms. Okay? You don't like that, Gert?
No, I'm just wondering if those people who, when you say they don't like this, maybe they would like you to call this the mode function of the single photon?
So mode function, of course, because this is the way I introduce it.
And if you look in your 2.4, the double linearity of quantum optics,
Yes.
the quantum Hilbert space of quantum mechanics,
Yes.
there's also a function.
Yes. But not a wave function in terms of the wave function of an electron, which gives a probability. Exactly. So I would call it a I don't know, state vector or something like that, because it doesn't give. Yeah, exactly. Not position and time, but number of photons. I don't know, thing like that. So, yes, but so here it's a wave function in terms of what French people call the mécanique ondulatoire, so the psi of RNT, okay? A wave function like psi of RNT, this one only, okay, the one which is in the Schrödinger equation. Yes. And so it is here, it is in this part of the thing. So people don't like it, for example, because you cannot build a delta function. So it's not a complete set of functions like the position operator for an electron, because you cannot concentrate energy in something which is smaller than the wavelength. Okay, so you cannot build something smaller. Of course, if you are allowed to go to high omega values or gamma rays and all that, of course you can focus. But if you stay at a given energy or around a given energy, you cannot localize a photon better than lambda cube, which makes sense. Okay, but I think if you, yes, the second thing is that people try to use it also not only for single photon states, but for many photon states, n photons. Okay, and when you try to find a wave function also for many electron states, it's complicated. You can do it, okay, second quantization and things like that, but it's tricky, okay? So wave function is well defined for an electron when you have only one electron. So in the same way, a wave function, quote, for a photon is well defined only for single photon, okay, not for more than one. So you can have other things if you go to 2 and 3, and other, like you have also for electrons, but in the second quantization approach. Okay, so this is not so important. Okay. Now I need to introduce something. I don't know if somebody has introduced it here in these 10 days or more, which is symplectic transformation. No, never? Ah, too bad. Because this will be helpful for the following. So 3-2 relation with, I need that, symplectic transformations. Okay, so there is a part of mathematics, which is group theory, continuous groups, Lie algebra, things like that. And inside this big thing, you have symplectic group theory, which is filling a lot of books of mathematics. Okay, so we want to use that a little bit. So I will just use it in the context here of what I do here, not general way. So it's a symplectic group is a group which preserves the laws of physics. Very wide definition, okay? So when you consider it at the quantum level, it means that it is a transformation which conserves the commutation relations, because all the quantum physics is related to that. Okay, and even more, because mathematicians like to have simple objects to deal with, it will be only restricted to the linear relations, which conserve the commutation relations. Okay, so if I consider an ensemble of operators B, so it's the same as the one I wrote somewhere here, okay, the column vector B. I have a transformation S acting on this A, which gives a column vector, okay? So my column vector is longer than usual. It's B1, Bn, if I use n modes, but also B dagger 1, B dagger n. Okay, so it's the extended version of the one I wrote before, because you have at the same time the B's and the B daggers considered in some way as independent things. So S is a 2n by 2n matrix, relating that to the an A dagger n. Okay, so S is symplectic, is okay when the, if I have what I wrote before, okay, A dagger J is delta Ij, okay, the commutation relation on this side implies that if I use that in this transformation, I will have B dagger J is delta Ij. Okay. Okay. So of course, not all the linear transformation here has this property. This property has the one for operators of transformation acting this way, and they are called symplectic. Okay, symplectic group. Of course, since something was written here, this is exactly what I obtained using my unitary transformation. Okay, so the unitary transformation has a subgroup of the symplectic transformation. They preserve commutation relations. This one is more general because, as you see, it mixes the A's and the A daggers. So the B's here will be linear combinations of all the A's and all the A daggers. Whereas the one I used, the unitary transformation, was only acting B as a function of A's. And of course, B daggers as a function of A daggers. But the same transformation. So S is bigger, is a bigger group. The group of S is a bigger than unitary one. Okay? So this, I stop here to just introduce the name. So then you can go to the books about this kind of thing and look at the properties of the symplectic group. There are some. So now I have a second thing that I don't know if you have heard of or not, which is Wigner function. Yes? It's okay? Not everybody? But here? Not here. Okay, but it's okay. Wigner function. Called W. Okay, it's a W of some parameter alpha. Okay. It's a quasi-probability function because it can be used to calculate the mean values of operators as a weighting function of the quantity. Okay, so if you want for example, A, mean value of A is W of alpha d alpha. So alpha is a complex number. Okay. A complex. It's like the alpha in the coherent state. Okay. Okay. So the mean value of my operator A can be considered as a classical mean value, calculated as a mean value alpha times the probability to get alpha. Okay. So you can do it for alpha dagger, for A dagger, for X and Y, which are combinations of and any other thing. So it looks like the quantum probability, quantum mean values are equivalent to classical mean values with a weighting function, W. The only problem, I don't know if it is a problem, the only feature of quantum mechanics is that this W is not positive, not always positive. Okay. So if it is positive, it can be assigned to a distribution of probability of some quantity. Okay. So the quantum fluctuation look like classical fluctuation with the weight, which is given by W. But since it is sometimes negative, of course, then this picture of quantum fluctuation is no longer valid. Okay. So the quantum fluctuations and the means around these quantum fluctuations have the same mathematical rules, but not the same physical content, because the W is not a probability.
It's real, it's not complex.
Sorry?
It can be negative, but
it is real. It's a real. Yes, real. It is normalized to 1 also. Because, so when you integrate W alpha without here, it is 1. So it is mostly above 0, because in order to get 1 as an total integral, so it has more positive parts than negative parts, but it can have negative parts. So this is for single mode. Then it can be defined for many modes. Then you will have delta of alpha 1, alpha 2. Okay, each one being used, for example, AI, AJ, the correlation function, A dagger J, for example, the one I introduced, is written as W of alpha I, alpha J, of everybody, of all the alphas, alpha I, alpha J conjugates D alpha. So D alpha being a short notation for this big differential for, okay? So I still use the same classical averaging with the weighting factor now, which is in the multimode case with a lot of variables. And I get my correlation function. But W is not always positive. Okay, and then if you look at the books, mathematics books about symplectic transformation, they tell you that the Wigner function is conserved through symplectic transformation, okay? Tell you that W in the new representation of the betas, beta 1, beta n. Okay, so this is the W that I can define with the B's, okay, and which will allow me to calculate means of the B dagger and all these quantities, okay. Of course, they are related to the W in the first one, okay. And the relation is that it is equal, but at a different points. That's, how do I write it? Of alpha 1, alpha n, here. So the Wigner function allowing to calculate means of the A's is the same as the Wigner function allowing to calculate mean function of the B's, okay? Just by a change of variable. So, where alpha L is the sum of ULM beta M. The U, okay? So if one wants to know the probability distribution, even though it can be negative, in the new variables, in the new basis, I take the same in the old basis, but not at the same point, at a point which is somewhere else. Okay? For example, with my transformation, which allowed me to go from 1, 1 to 2, 0 minus 0, 2, here it would be the sum and the difference of the arguments. Okay? So this is important because if it is not always positive in the first basis, it's not always positive in the second one because it's the same. Okay? So the negativity of Wigner function is intrinsic. Okay? This is very important because people attribute a lot of meaning to the negative parts of Wigner functions. And if in an experiment you are able to show, to determine Wigner function, which is something which is done in many labs, and you are able to have a very negative value of the Wigner function, you are very proud. And then you have a Nature Photonics paper. And okay, this is good because it's really a nice property which doesn't depend on the basis. Of course, the point where it is negative and the area in which it will be negative is not the same in the two. Okay, so this second part. And then there is another one, which is the purity of the state. So now it's, so this you know also in quantum mechanics. When you go from psi to cases where you do not master the total state of the system, okay? Like this morning I spoke about coherence, in which you do not master the classical part. Here, sometimes you do not master the quantum one, so you have to describe it in another context, rho, the density matrix, which allows you to describe in the same way, in the same mathematical tool, the classical aspects of the fluctuations and the quantum aspects of the fluctuations. Okay, which is very nice for that. So you can include here the lack of coherence due to the fact that you do not master the field at the classical level and the fact that there are quantum fluctuations. And what is an important parameter is the purity, because this is called a pure state, and this is called usually a mixed state. Okay, the purity is trace of rho squared. So if it is 1, trace of rho squared is 1 means that you are in this case, in the case of a well-defined quantum system. If purity is different from 1, if smaller than 1, the quantum state is mixed, has some classical incoherence, let's say, in this. So it's important. It's not only the incoherence linked to the quantum fluctuations. Okay? A trace of rho squared, you can relate it to the Wigner function. Trace of rho squared is okay, don't write it, is the integral of the square of the Wigner function. Okay? Over the whole space. So if you integrate the square of that over the whole beta space, it's the same as integrating this one over alpha space. And then trace of rho squared is independent of basis. Okay. So related to W squared. So then intrinsic. And I will stop my my list of intrinsic things here. Okay. We have the single photon, the vacuum, single photon state. Wigner function, purity. Okay, you can try to find others. Okay, so we can stop a bit. Okay, may I go? Let me go to single mode states. Where do I? Here, okay. Three. So intrinsic single mode state. Remember that in the classical part, single modes, classical fields were something interesting because they gave rise to perfect interferences. So is there something related or analogous here? So I will call it intrinsic if there exists a mode base. So I have some state, okay, and that I can write in any mode basis. And if there exists a mode basis in which I can write psi1 as something in a given mode 1 times 0 everywhere, okay? So I can put all the quantum part, non-zero, non-vacuum quantum part in a given mode. What I did for the single photon state before, okay? So is it possible to have other states at the single photon belonging to this thing? Okay, the question. Let me go another example. So the first one was single photon. So the single photon, which looks multimode, is actually single mode in the right basis. Now I take the example of, wow, alpha 2. Okay, all these are coherent states. Okay, I take a psi alpha, I don't know how to call it, which is a multimode coherent state. A coherent state which is a product of coherent states in all bases, in all modes. Okay, meaning that I have a L, alpha L, equal to alpha L, alpha L. Okay, coherent state definition, but now for all the modes. Actually, this is a single mode state also. is single mode. So here also it's a demonstration that I skipped. It's very easy. So if you take the mode defined by, so this mode is correspond to FL. So sorry, I didn't put the mode. I should, because for a single photon it depends on the basis, but for coherent state also. So sorry, I should have written more precisely. Alpha 1 in mode F1, etc. Alpha L in mode FL. Okay, and so on. So is single mode because if I take the basis that I call G0, so not the basis, but the mode G0, which is a combination one of beta L of some, one of a beta of some of alpha L FL of RT, and beta being such that beta squared is the sum of alpha L squared. Okay, so I start from this state, okay, written in a given basis. Now I define a new mode as a linear combination as the old ones. The linear combination being this with coefficients which are the alphas of the coherent states, okay? And then I normalize it because it has to be normalized to 1, so beta squared. Okay, and then you can show easily that this same state is a coherent state beta in mode G0 and nothing else, and 0 everywhere. Okay, so you can put all the quantum things for the coherent state in a given coherent state. Okay, so a mixture of coherent, not a mixture, like a tensor product of coherent states is another coherent state. Okay, so this you can define that for pure state, but also you can do it for not pure states. You can say rho is single mode. If there is a basis on which you can write rho as rho 0, a density matrix in the given mode, times the density matrix of vacuum, which is 0, 0, for all the other modes. Okay. Okay, so this is a definition. Here it's more, it's just a state, not only the. Okay, this is useful to account for the classical coherence, which will be described by that. Okay. So there is a mathematical property of single mode states, is that I take a taste basis. So I take one basis among, and it's my choice. Okay, I take the, and then I look at AL psi. So I apply AL on the state that I want to show whether it is single mode or not. Okay, so I have a list of vectors like that. Okay, so if are all proportional, if n alpha is equivalent to psi single modes. Also, I skip all the demonstration, but it's not difficult. Okay, if you have your state, you write it on some basis, so it looks ugly because it's not the right basis. Okay, you apply all the ALs. You have your list of AL in a given basis that you choose. So you have a list of vectors. If they are all proportional, it is single mode. Okay, so you can verify that it works on these two. On this one and the single mode. Remember the single photon state was the sum of Cn1, okay? If I apply AL on this basis, AL will destroy photon, so it will go from 1 to 0. So 0 is the same for everything, so I put the 0 outside, and then I have just a number. So they are all proportional to the vacuum state. So it's single mode for the single photon. This one, when you apply A to that, you see it, you have this property. So you have the same state with some coefficient. So they will all be proportional to the initial state. There will be eigenstates of these things. Okay, so this is also single mode. So this is a state, and it is, so this is here. It is the same also for rho single modes, equivalent to AL rho of dimension 1. Okay, this is the ensemble of vectors, of operators now. AL rho, because rho is an operator. So AL rho is product of two operators, it's an operator. So it's a big thing. It's an n by n thing. So it's more difficult to have matrices which are proportional than vectors which are proportional. So it's more difficult to be single mode for in this case, which makes a good connection with the classical part. Because if you remember, if a field is completely fixed in classical domain, it is single mode. Okay. And then here also I skip my demonstrations. It is also equivalent to say things about G1. Okay, now my G1 of, remember it was one important, was something related to a mean value among classical fluctuation. But of course, I can take the same with quantum fluctuations and the corresponding operator. So here it will be E plus dagger, okay, the corresponding quantity with the conjugate of R and T, E plus of R prime, T prime. Quantum mean. The one you can calculate with Wigner function, for example. Okay. So sorry, I did. So this is just definition, okay, and it is equivalent not to that, but to the fact that the small g1 is 1, whatever r prime, t prime. So we extend to the quantum domain the property which was the property of single modes classical states, classical fields. Okay, so in a single mode quantum field, fulfilling this mathematical property, if you use that and put it in this expression, you find that. Okay. So what does it mean? So it still has the same meaning for the physics, meaning that it is perfect interferences. Okay, perfect interferences. And you see the single mode state is defined by its mode, of course, but also by the quantum state in which it is. Okay, phi 1. Phi 1 can be Schrödinger cat, a squeeze state, whatever. Very complex, a single photon state. Okay, and so this property is a property of single mode fields independently of what you put in the mode. Okay, so this is true whatever phi 1 in the mode, or whatever rho 0 in the single mode. In other terms, it's a property of modes and not a property of quantum state in my drawing of quantum optics. So it's optics part, not quantum part. And when was it? 50 years ago, a bit more now, I think. There was a very important summer school here where there was a lot of very famous people, including Glauber and Kroll and Kessler and Cohen-Tanucci. It was organized by Cohen-Tanucci. And it was a place where Roy Glauber delivered this main message about coherence and quantum explanation of coherence and all that. And so it's very interesting to read this paper. So I assume it is here if you look at the proceeding of that in the library. So it's a very interesting papers written by Glauber. Actually, there are not so many papers written by Glauber. Yes?
And do you know that there were two Italians who wanted to listen, but they were not admitted?
There was
told them no, go away.
Bonifacio and
Tito
Araki, yes. There was, yes.
People who became very famous.
Also, yes.
They said, we don't want to eat, we will be quiet, we want to listen.
Not enough.
Gave his lecture in the hotel.
For them, after, okay.
He gave each lecture twice. Very good.
Okay, and he said, so he looked at interferences that can be produced by quantum fields, and he found that, so he wrote things exactly like that, and he found that perfect interferences can be achieved by single photons, okay? Because so he didn't say it the same way as I say it here, but it's the same property, okay? What is important is it is in a single mode, okay? And a single photon is always in a single mode. So it seems that a single photon is not very coherent, but still it produces perfect interferences, okay? So this is what we find here. So it produces, you take a Schrödinger cat here, you have perfect interference. Take a coherent state, of course, it's... So the coherence of the field, in terms of classical coherence, quality of interference effects, is related just to the mode, okay? Okay, so now we have an experiment. We want to know whether the state that we have produced is single mode or not, because it's important, okay? How to do that? You see that this kind of rule is not easy to... You can do it because AL, to remove a photon on a state, it's feasible, okay? You put a beam splitter, then you have a detector. When your detector clicks, it means that you have one photon less because it has been destroyed at the detection. So you can do that, but then you have to apply AL, so a lot of clicks in different modes. Okay. Difficult. This one perhaps easier, but what is easy, not easy is this part. You have to do it for any couple of points, okay? So it's difficult also. We will see that on the covariance matrix it's possible to do it, but you can find some sufficient condition. Okay, something which tells you that I'm sure that it is not single mode, okay? And then that is more complicated than single mode physics. And so, because if single mode, then there is only one variation. So if it is single mode in mode, what I call it, G0, okay? It's single mode in mode G0. So everything varies like G0 of R and T. Because it's only, so the field is E plus is G0 times something, okay? So all the temporal spatial variation is in the mode, not in the field. Okay, so everybody varies the same way. Any observable, for example, the mean values. So of course the mean values varies like G0, but also the variance, because the variance will have this kind of factorization term also. So variances or root of variances vary in the same way as means. Okay, so if you make the ratio between the variances and the mean, if it doesn't depend on the point where you measure it, then it can be single mode. It's not sure because there are other tests. But if it is not proportional, it means that means and variances do not vary the same way, and then you need at least two modes to account for that. Okay, two variations. So this is simpler. Okay, and I will show you. I don't know if yes, I will finish that first, but I will show you that there have been experiments on that. Okay, showing that quantum state produced was not single mode. Okay. So this is sufficient condition, but of course it's not enough. We want to have more information. And more information comes from covariance matrix. And do I have to do that before? Yes. Okay, so 3, 4. I can just expand my intrinsic single mode by intrinsic n modes. So intrinsic number of modes. Okay. So it's just an extension of that. And an n mode state, intrinsic n mode state will be an intrinsic state in which I have something non-zero spanning over n modes, and then zeros after. Okay, so there exists n mode state and big N modes states is a state which can be written in given basis, in the right basis, psi, not phi n, okay, which spans over n modes, and then zeros. Okay, I can put everything in n modes. Sorry, here I forgot to mention something. I go in my examples. Of course, it's good to have a counter examples also. Okay, because here it seems that all states are single modes. Okay, let me consider the state 1, 1. This two-photon state, which looks. So we know it's a two-photon state. So it will be an eigenstate of 2, but can it be 2, 0? Okay. So I use this rule. I apply a annihilation operator on this one. Okay. If I use the first one, A1 acting on 1, 1, gives me 0, 1. Okay. I destroy photon here. A2 acting on 1, 1 gives me 1, 0. And these are not proportional to each other. Okay, so the 1, 1 state will never be put in the 2, 0 state. Okay, it's not possible to have your two photons and put them together. What you can do is what I showed before, is 2, 0 minus 0, 2. So you can put them together, but you don't know in which side, on one or the other. This is an Mondale experiment that you know. I think once you put one photon and one photon, then you have a transformation on the beam splitter, which is a unitary transformation. So it's the same as a mode basis stage. And then you know that it gives 2, 0 here or 0, 2 here. So never 1, 1, so never clicks. Never common clicks. Okay, so this was just to show you two-photon state. This one is a real two-photon state because I can write it on two modes here and nothing else. Okay. Okay. Of course, it can be done also on, at the level of density matrix. Yes, something I also have a bit of time. So I can. So remember, we started from psi 1 sum over Cm 1 in mode Fm 1. Okay, which is single mode. What can we say about the state rho 1, which is a mixed state, looking like this one? So this one is a little bit like probability Cn squared to have single photon in mode Fn. We know it is not that because there are phase relations and it's more than that. But we can consider now the mixed state, which is 1 Fn, 1 Fn. Okay. I take a single photon pure state in a given mode Fn, and I make a statistical mixture of these with probability Cn squared. Okay? So it's very different from this one. Is it single mode? Can I put all this uncertainty in a given mode? Okay, we just apply the, so here also I don't make the demonstration, but you use this rule. You look at AI rho, so you destroy one photon. Oh, it's easy. Okay. You destroy a photon, you will have 0 here. but you will still have one Fn here. So this quantity depends on the mode you consider, so it will not be just a number in front of it. So it's not single mode. Okay, so it's only the coherent mixture of photons which is single mode. The incoherent mixture, the mixed state, is not. Okay, so it relates to classical coherence of light. And it's true, of course, for any other mixed state looking like that. Any other? I'm not sure. I've not seen any demonstration. But okay, I guess it is. It's perhaps something for tomorrow also. We can try to make the demonstration. Okay. Okay. So how to characterize that? So I remove my examples that I should have done before. So I go back to the intrinsic number of modes. So this can be shown to be equivalent to the fact that if I apply AL on psi n, okay, it's the same thing, but now I apply it on this one. Okay, this list of things spans a space of dimension n. Okay, it just generalizes what I've written here. When they are proportional, of course, they span a space of dimension 1, of course. And here, you have these two. They belong to a space of dimension 2. Okay? So this is just a mathematical property. So I've tried a lot to find something like that, sufficient condition for two-mode state. I've tried to relate two-mode state to G2 instead of G1. Because 1, 2 doesn't work. So not easy to have characterization of an n-mode state, except that it is more than 1, so more than the one giving perfect coherence. But there are some mathematical property. Let me define the coherence, classical coherence, the complex coherence that I have defined before, but now at the quantum level. So I take my C that I call Cnn prime, and which is E minus, so E plus conjugate of Rn Tn, E plus of Rn prime Tn prime. Okay, so this is the G1 here that I take. So I have a list of points. I take a list of points which are labeled by the n, and I take n, so n and n prime varies between 1 and something which is the number of points that I consider. And so I call it ng in my text, so a number of points in the grid. So I take a grid of points like a CCD camera or sampling device for time, okay? I have these points. And from that, I consider the matrix, okay? A bit like in the classical experiments for the transmission, but here is for the coherence matrix, covariance matrix, okay? The one that I showed that it is transformed like the basis transformation, okay? So this is a matrix. CNN prime is an ng by ng matrix. Another thing that can be shown is that the number of it can be diagonalized because it's an Hermitian matrix. Okay, when you take n prime n, you have the complex conjugate. So its Hermitian matrix has real eigenvalues and can be diagonalized. So the number of modes is bigger than the number of non-zero eigenvalues. This can be demonstrated. This is more physical in some way. So you take points. You can take a number of points which is not big. It's not like here where you have to take all the values. Okay, it's not possible. Here you sample your field, your state. So you have this matrix. You diagnose the matrix. It has some part. Of course, if it is an n-mode state, it will give 0 everywhere, except in the little corner where you have this thing. Okay. But we know that it is like that. Of course, when you sample it with a fixed and limited number of points, you can miss some kind of complexity in the details. Okay, so if you explore the system with a grid which is too loose, you will not see all the details. This is why it is the real number is bigger than the number you measure. Okay, of course, if you take a single point, you will find one non-zero eigenvalue, and it's not enough. Okay, you need at least more points than the effective number, but the higher the better. We'll go back to that in the experiments that I will show you later. Okay, so we have something to deal with here. Okay, questions on that? So now I go to description of some experiments. Okay. Yes.
Can one say that the thermal state is also intrinsically single mode?
The thermal state, we'll go back to that also later because I don't know if there's, of course it depends. You can define it as the one that a little bit like, where is it? As a density matrix rho. Spanning over, I don't know. Of course, you can put, what is sure is that you can put thermal state in other modes. Is it possible to put all that in? So you have to apply this rule. It will not be simple. I mean, if you apply A, so it's e to the minus beta h, yes, rho. I don't know what is the action of A on that. Okay, there are many questions. It's good. Yes. Okay, so tomorrow morning, a lot of things to. Okay, I describe some experiments. Okay, this first thing is just to remind you, okay, quadratures that. So I didn't speak about quadratures at the quantum level here, but of course you remember that at the classical level there was a real and imaginary part. So at the quantum level is the same. So the the AL operator, which is corresponding to the field operator, you can write it also as XL plus IPL plus IYL, okay, which are emissions. And you have the commutation relation XL/YL prime, which is 2I delta LL prime, okay, that you derive from A dagger is 1. And so since you have something looking like commutation relation of position and momentum, you have the same Heisenberg inequality relation telling you that you have noise, okay, you cannot measure with perfect precision the two quadratures. Okay, so this is a well-known part also of quantum optics. If you look at two modes instead of one, you see that these relations, A dagger, AL, A dagger, L prime is 0 when L and L prime are different. So there are no quantum restrictions to means and to correlations between two. Okay, so you can have perfect correlation between different modes, which is interesting for applications. Okay. You can have fields like that, in which you have some, okay, two squeeze states in each mode, not correlated, is first thing. But you can have fields like that, where in each mode you have fluctuations, big ones. Actually, there are thermal fluctuations, but you have correlations. You have each time you have something going here like that, you have the same here. So you are fluctuating like that. And each time you have something here, you have anti-correlation on the other. Okay? So this is another state of light, which is called EPR, Einstein-Podolsky entangled state, with a lot of quantum correlations, both on X and Y, so both on position and momentum. So this is the one which was the object of all these arguments by Einstein, Podolsky, Rosen, and others. And the state that Einstein, Podolsky, and Rosen gave as an example in the paper was exactly the one which is produced in quantum mechanics. Just the difference is that they were considering position and momentum, and here we are considering quadrature of light. Okay. Okay, so I will go back to that tomorrow. So this is one of these experiments. The first one, actually, it was when was it? A long time, almost 10 years ago. And Gert, I forgot to show your experiments in frequency domain. Sorry.
I forgive you.
And so this one is a quantum property of this kind of system, which is optical parametric oscillator. So we are back to the previous conference. Since the photons are created by pairs in a parametric medium, okay? When you have a pump photon, it creates signal and idler photons in the same process, they are perfectly correlated. So when they go out of the system here, you have a signal field which is fluctuating, because the photons are created in a random way by the process here. They are also random in the other, but it's the same randomness. Okay, the intensity, the arrival of photons is the same in both. Okay, so it's a state of light which looks a little bit like this one. Okay, except that I'm measuring only one thing, which is intensity. I'm not measuring the two. Okay. Okay, but then in order to see that, I look at the variances of the difference between the two. If this variance is very small, it means that the fluctuations are the same. Okay. And I want to see whether this state of light that is produced here is single mode or not. Okay. So it depends. Actually, it depends on the cavity which is put here. Okay. If you put a cavity which is confocal, you remember that the distance. Sorry. Thank you. The distance between the two mirrors is equal to the radius of curvature. This is confocal cavity, so it sustains at the same time many transverse modes, half of the transverse modes. So it's multimode. And so the photons which are created in this way are likely to be in a multimode state. Okay? If you change a little bit the distance, you are no longer in confocal. So the modes are separate, and there is single mode. So then the system is likely to be in single mode case. So in order to see that, one changes the amount of light which is going here and here by a variable iris, so something you close and open. So you change the spatial properties. I mean, you sample in a different way the spatial properties of the state, okay? And you can make then the ratio between the mean of that, so just the intensity which is transmitted, and the fluctuations. And you see what happens. It turns out that if you do it in the confocal position, you find this kind of points. So the experiment was difficult, so it's a lot of dispersion. But it's truly very far from this linear variation, which would be the variation of in a single mode case. And if you change by a few fraction of a millimeter the distance between the two mirrors, you have this line, meaning that this is. You are not sure it's single mode because it's not. You have not made all the demonstration, but you see the clear difference between this and this. Okay, so this one is for sure multimode, and this one is likely to be single mode. Let's say. Nothing prevents us to think that it is. Okay, so this was a. I don't remember. Gert experiment was in the same kind of thing, but in frequency domain. So by looking at a part of the frequency spectrum of the state or the total spectrum. And more recently, there was an experiment performed NIST labs in Gaithersburg by Follett and others, creating also twin beams, two beams with perfect correlations in nonlinear effect in atomic vapor. So it's four-wave mixing in this kind of thing. So when you send a very intense palm beam in a rubidium vapor and at the right wavelength, close to the resonances but not too close, and you send a seed here, you produce a conjugate beam like in Chi2 medium, but now it's a Chi3 medium. And these two are quantum correlated. And the effect is there is no cavity, very intense effect even without cavity. So there is no mode filtering by the cavity. And they did the same. So there are two beams. As I cut the two beams in this way or in symmetrical way, okay? That's removing. And looking at what remained of the quantum effect at each time. And you see that if it was single mode, it would be on this line. And it can be achieved in, okay, you can achieve the single mode operation also, and then give this line. And if it is not single mode, then you have this or this, okay? So it's another curve. So this system that is here is not single mode also, which is, makes sense in some way, okay? It would be very strange if it would be one single mode. Okay. Since I've given you 5 minutes break, no, we have to go directly to the dinner. No, okay. I have 2-3 minutes more. It's okay? Okay. So it's something we did rather recently with Julien, Laura, and the PhD was Olivier Morin. So how to not only measure the number of modes, but find the mode in which it is. So now it's temporal mode of the system. Okay, this the mode of a single photon, which is produced by the heralding photons. What does it mean? You take Chi2 crystal. Now I am at the single photon level, not squeeze state and things like that, just single photons, okay? So, and sometimes the pump on the Chi2 medium produces twin photons, okay? Two photons, which are produced at the same time. So we not go to what are the modes of that, okay, which is important. But here I just measure in the right way the photon arriving on this side, okay? And of course, if I have a click here, since this is produced by correlated mechanism, then I'm sure that there is another photon at the same position in space or all the codes that you want. So I will have an heralded single photon state because it's not deterministic. I don't know when it will be produced, but when it is produced, I know. Okay. So if I condition all the experiments after to the measurement of photon here, I post-select the events where I have a single mode state. In which mode? It is my problem. So it depends on how it is produced here, of course. Okay, so let us look more precisely at the experiments. The art of the system is the OPO here. So it's not this kind of shape that you showed. Okay, it's a linear OPO, a type 2. It's spawned by a very stable laser. And so it produces photons, signal and idler photons, which is type 2 in orthogonal polarization. So one is going this way, and the other one is going the other way. So we have, first to herald, to know the photon in one of the two paths. This path, heralding path is this kind of thing. But of course, if we just put a photon counter here, we don't know in which mode the photon will be detected because a photon detector collects all the light coming from all directions and all frequencies. So we have to filter first a lot. So there is an interference filter, a Fabry-Perot filter, which takes a very, very narrow band of the spectrum, and then in a special way, we select a mode by a single mode fiber. Okay. So at the end of all that, there is a photon counter, which is a SSPD, a single superconducting single photon detector. So it's a cooled detector at helium temperature, which is a very low dark count rate. So it's not very good for quantum efficiency, but very good for dark counts. So we can accumulate signals. Okay, so when there is a click here, it's a click in a very well-defined mode. Okay. And then on the other side, we need to measure the state of light which is produced here in a most perfect way. And the way it is done is to use Homodyne detection. Okay. So we will see tomorrow more details of Homodyne detection for multimode systems. So, but you know what it is. Okay, you mix the beam to look at with a local oscillator, which comes from the same lasers at the same phase variations. And one looks at the difference between the two, and this enables us to reconstruct the whole Wigner function. Because Wigner function is enough to describe perfectly the state of light. Okay, so it has all the information, which is why it is nice. Okay, and since it is heralded, one will look at the Homodyne detection only when it clicks on the other side. Not only exactly at the same time, because there can be some time delays because you have the cavity OPO. So when the two photons are created at the same time, then they bounce in the cavity, and one can go out of the cavity at some turn inside, either before or after the other one. Okay, there is a little bit of time decorrelation between the two. So when you click here, you are not sure that the other photon will be a little bit before or a little bit after. So the best is to count all the photons, all the events here, okay? And then when you have a click, you look a little bit after and a little bit before also. So it's real post-selection. Okay, so this is what is given here. You have the signal coming out of Homodyne detection. And you look at times here, either before or after the thing. And what you measure, what you determine is this covariance matrix. Here it's a real covariance. I mean, it's a little bit in between, but it's a covariance matrix giving you the intensity correlations at 2 different points. Oop. So here I have my time bins. So this is a time bin on the SSPD. Okay, so I have a click here. I look at the other side, but I look at many time bits, 1,000 time bins, 500 before, 500 after. So I have 1,000 samples. Okay, and then each time there is a click, I have 1,000 sample, and so I can average over all that. Okay, so it's a time average, which is equivalent to an ensemble average of the system. And then I calculate, Olivier did the calculation of all the correlations between all these time slots. Okay, so it was able to have all the UI, UJ mean averaged correlations that you can put in a big matrix. Okay. And the big matrix, then you can diagonalize it. It's a 1,000 by 1,000, but okay, no problem. And you find that, so look at just single photon, the green one, okay? What you find is a series of values close to 1, close to the vacuum level. So there are the vacuum states. Okay, here the vacuum states do not correspond to 0, but to 1, because in vacuum state you have vacuum fluctuations of the quadratures, okay? So you can remove this one if you want to go to the 0. So, and you see that from that thing, you have a big peak at the beginning, which gives you the mode which is filled in some way. All these modes here are vacuum modes, because they have vacuum fluctuations. This one is full of something, okay? And then after a while, it goes down. This is just, experimental technical reasons of bandwidth. So for long time, it doesn't work so well. Okay, so it should be around 1 also. It cannot be below vacuum level, obviously. Okay, so the important thing is that If the system would not be single mode, there would be more than one big peak, okay? And if there are 2 or 3 peaks, we would know that the number of effective modes is bigger than that, okay? Here we know that it is bigger than 1, but okay, it makes sense that it is 1. So this, now we know it's single mode. I mean, we have very good reason to think of that. It's not perfect, but because we didn't sample with very, very high efficiency, of course, very high resolution. But then we know the mode, because the mode is an eigenstate. I remember that when you calculate this kind of matrix, then the mode change is the change of basis with diagonalities is equivalent to mode change. Okay, so we can calculate the mode as being the superposition of these time bins with the coefficients, which are the coefficient of the eigenstate. And this is what you find. For single photon is a green line. So, and the theory would give this one, okay, the black line. Oops. So this is for tomorrow. No. Okay, so we have, it was the first time that we had this experimental determination of the mode in which the state is, okay? A lot of people derive that directly by theory, okay? What is that? It is just as I told you, the 2 photons are decorrelated by the cavity time. So one goes out at some time, the other one another time. Of course, the time delay between the two is not very different from the cavity time, of course. So actually the temporal mode of the cavity has this form. So when it is triggered, of course, when the photons is, it is a before and after with a time which is cavity time. Okay, so this would give this peak here. Actually, in the experiment, of course, the peak is cut a little bit because of also of resolution problems. Okay, so this is what I promised. Okay, I stop here. Thank you.